to the very first episode of the Space Show. Yeah! The Space Show is going to be a series of scientific videos, each one teaching you about a different topic. Today's topic is, what are the four fundamental forces of the universe? And are there more than four? So we'll start with my first question. What are the four fundamental forces of the universe? So as you can see here, the four fundamental forces of the universe are gravity, the strong force, the weak force, and the electromagnetism, and some artwork that scientists like to put with them. But what are those circular thingamablobs they put right next to the artwork? It turns out that those thingamablobs are referred to as bosons. Different forces have different bosons, but the bosons are the carriers of the force. Without the bosons, the forces wouldn't have any effect at all. We'll start with the strong force. The strong force has a kind of boson called a gluon. There are 8 separate types of gluons, but they all carry out the strong force. They're the things that hold atomic nuclei together and hold quarks inside protons and neutrons. They also hold mesons and baryons together. On to the electromagnetic force. The boson for the electromagnetic force is the photon. Photons are used non-stop in atoms. Photons create light, used often in chemistry and electronics. Without photons, the universe would be pitch black. Photons also carry out the electromagnetic force. So next time you're building an electronic device or using magnets, if it weren't for the photon and the electromagnetic force, there'd be no point in doing anything at all with it. Next, we have the gravitational force. The boson for the gravitational force is the gravitons. The reason why there's a question mark in that image is because they've never been seen before in science. But we know that they're there because the gravitational force has got to have a boson. Without gravity, the whole universe would explode. Also, gravity is what holds the Earth together and other planets together, and holds the solar system together and creates black holes. Gravity also holds galaxies together and galaxy clusters together when normally they would fly apart. This is because of dark matter that has a gravitational force 3 times that of ordinary matter. On to the weak nuclear force. This is what makes the sun burn. It creates neutrino interactions. It triggers radioactive activity. Actually, I'm not so sure about that one. I thought electromagnetic force triggers radioactivity. But anyway, the weak force also triggers neutron decay. Oh, and did I mention that the strong force also gives quarks their color charge? Quarks and leptons are both 2 kinds of particles that these forces act on. The strong force acts on just the quarks. The electromagnetic force acts on atomic nuclei, trying to rip it apart, but the strong force stops it from doing that. And the electromagnetic force also affects leptons. The gravitational force affects everything. And the weak force affects quarks and neutrons. Oh, and don't forget about mesons and baryons. For years, scientists have been working at the possibility of creating a new kind of boson called a Higgs boson, first thought up by some guy who had a last name of Higgs. Yeah, he invented the idea, and well, people have been trying to create this Higgs boson by smashing protons really fast at just shy of the speed of light. But so far, the only thing they've been getting out of these super fast collisions is neutrinos and quarks and unstable fundamental particles. Not fundamental force bosons, fundamental particles. They are two entirely different things. But maybe someday they'll make a Higgs boson after all. But in the meantime, let me show you what a Higgs boson would do. So, let's say that those green dots are the Higgs bosons in the Higgs field that penetrates all space. Now, what happens if a particle enters this field? Well, the Higgs bosons would rush over to the particle. Just like people will rush over to a celebrity if one happens to walk in the room. In this case, the people can represent the Higgs bosons. You may think that the particle's gravity attracts the Higgs bosons, but actually is the Higgs bosons that give the particle its mass. And without its mass, it wouldn't even have gravity. So you could say that the Higgs field is like a fifth fundamental force using Higgs bosons for a boson. But then, after that, there's dark energy, the sixth fundamental force. But perhaps it is dark energy that is the most important of them all. Dark energy is the opposite of dark matter. Instead of dark matter's gravity pulling things together, dark energy is pushing things apart. In a universe like our own that has dark energy in it, there are three possible outcomes. The first possibility, shown on the left, is known as the Big Crunch theory, where either dark matter gets stronger than dark energy and pulls the universe together, or that dark energy reverses and starts pulling things together. The second possibility, shown to the right of the Big Crunch theory, is known as the indefinite expansion theory, or cosmological constant, where dark energy keeps pulling things apart at the same rate over time. But then there's the third possibility, called the Big Rip theory, shown on the right. This is the most likely theory, is that dark energy becomes unstable and pulls the universe apart faster and faster some 10 trillion years from now, until a Google years from now there is absolutely nothing left in the universe. That's all from today in this Space Show episode. Join us on Tuesday, 26th, 2012 for our next episode. Our topic next week is it possible to go faster than the speed of light? See you then!